Yeah. Sorry about that. Thank you for that reminder.
Yeah, thank you. So we did not record a PowerPoint presentation, but I'm going to start here from zero, from the hands-on session in Imaris. So this is the recording here. So if you've opened up Imaris, and let's say you've never used Imaris, you know, this is how it looks like. This is what we call the arena view. Okay. These are the demo images. So these come automatically installed with Imaris itself. So if you want to play with one of those in your free time, if you don't have any images yet, those are available to you at the workstations as well here at Emory. And this is what the arena is. So if you want to look at your specific folder, you can click on Observe folder and find your folder. Like, for example, I have on my desktop this Emory Workshop 2023 folder that I created. So you can go in here and add it. You say select this folder and it adds this folder, like you see here. Here's the folder. It adds it to your preferences, so to say. Just making sure you don't want to clutter it with Imaris seeing everything on your workstation. You just tell it what to see and what not to see. Okay. So if you have like some data, you simply double click on the data and it will convert. Okay. Taylor, are you okay if I just throw it on your data real quick? Yeah, because I did work with Taylor before here. So this is Taylor's data. So I will revert quickly to original image. So this is what it looks like. This is a 3D image. You see this little arrow here. It means it has not yet been converted. It's an ND2 file. Okay, so an icon file. So if I double click on it, you can see on the right hand side, it's converting here 50, 60, 70%. And once it's converted, the arrow is gone and it's already in the Imaris file. Okay, so very seamless. You double click again and it opens up in the 3D environment. Okay, so that is how you convert the files. You can also click multiple and then convert them together, or you can use the separate Imaris file converter, which is a free tool that you can install on your workstation to pre-convert or in batch pre-convert a lot of files before going to the Imaris workstation. Okay, so demo images. Again, I'm going to start with this image here. Okay, so we have vasculature in the red channel and microglial cells in the green channel. The main view, the viewer here is the main part. This is where we interact in the 3D environment. We can rotate, zoom in, pan, like a typical tools for interacting in the 3D environmental software. We have this floating window here that's called the display adjustment. Okay, we see our different channels, red and green. We can turn on and off individual channels here. We can adjust and change, you know, intensity, contrast, gamma value, those kind of things here, you see, by playing with the little dark triangles here. This does not change your like raw data. It's just for visualization purposes. So you're not gonna get a different segmentation here than here. It's just how you look at the data yourself, okay? And how you want to create your image. Then we have on the left-hand side here, we have what is called the scene. Okay, this is where we create our objects. You see little shortcuts here, very tiny objects, very tiny shortcuts for spots, surfaces, cells, and filaments, like we've seen in the presentation. If you click on any of those guys, okay, you find the settings of those. Like for example, in volume, you can see the 4 rendering modes that we were talking about in the presentation, like blend mode. Here's the MIP, the maximum intensity projection mode, or you can go to frame. You see the line width. You can increase the line width and decrease it, and a variety of different statistics based on what you have highlighted here. Okay. We can add slicers as well. For example, an author slicer here with the shortcut add new author slicer. This allows us to slice through the data set. Okay. We're still in the 3D environment, but you can slice through it. Or you can use this guy here, slice position on the left-hand side. You can grab the arrow and change the orientation to go to YZ or XZ plane, or simply clicking here. And then just slice to a different plane. Or if I delete this guy, you can also use an oblique slicer, where you're not restricted by any of the orthogonal directions. So you can choose an arbitrary direction and slice through it. Okay. Any questions so far about just the basic environment of Imaris? Because now we're going to jump into creating some of the objects. Okay, so I think we'll have probably enough time to create the spots before we break for lunch. Okay, so the researcher, what they want to do is they want to look at the microglial cells. They want to count them. How many of those cells do I have? Okay. So we're going to use the spot object to count. Okay, so let me see. Choose first.
I really love the OP cipher percent.
Okay, so again, this researcher, thank you. The researcher wants to count how many of those microglial cells I have. So in terms of counting, we're going to use spots as a basic tool because we're not interested in morphology, or this researcher is not interested in morphology, at least at the beginning. We want to do some spots, okay? So we click this guy here, add new spots. It creates us the spot object. The default name is spots1. And my tip or recommendation is to always double click on the name and rename things. Okay, so instead of spots, I'm going to call this microglia. Okay, if I don't have much going on, it's not a big problem. But imagine you have 20 surfaces or 20 spots, it can get confusing. So which one is which? Okay, it's just something that I always do. It's very helpful here. Okay, let me see if I can bigger. Nope. Can I make this? Don't know if I can make. Is there a way to do full screen? I should be aware, right? Zoom. Live on YouTube, yes. Or here in view. Yeah, full screen. Yes. Yeah, I think that's perfect. Thank you.
Sorry about that.
No problem. So I'm gonna call this microglia, okay? And then this is what the wizard is, the creation wizard. You can see on the bottom left-hand side here, where it's blocked from the pen. It should say 1/4. So step 1 out of 4. Okay. It means it will take 4 steps for me to create my object to count how many of those microglial cells I have. Okay. There's a question?
If you want to make a movie, for example, one of the vibration for the job, you do the overlap with the image in the same imaging, or you will create a series image. How do you do that?
I mean, it depends on the microscope. Typically, like if you have, I don't know, like size, let's say, like you can create, it creates like a time series. It's one file. You import in Imaris, and it's already a movie in Imaris directly right away.
One file,
Mm. Yep. Okay, so step 1 out of 4. So we have like a few things where there's checkboxes. You know, you can skip automatic creation and go and edit manually. I'm not going to do this. I do want to show the automated creation. We have the possibility to segment only a region of interest. Okay, so I'm not going to do it, but I do want to show it real quick. So I click this guy. Why would we want to do a region of interest? There's maybe 2 main reasons. So your data set, first, maybe you are interested only in region of interest. Maybe you care only about the top half and not about the bottom half for some reason. So that's a good valid reason. Then you click segment only region of interest. But also maybe your data set is really large and you want to quickly look at only a region of interest, like a little 1/4 of it. And then you do check here, process entire image finally. So you can work on a small portion, do your wizard the 4 steps, and then you click process entire image finally, where you take a coffee break or lunch break and come back and hopefully everything is done. It's if your data set is really, really large, or like you have a laptop like me and your data set is on the larger end. So I'm not going to do this one, but I do want to show with segment only region of interest. If I click the blue arrow and go to second step, then I have the possibility, you know, to do my region of interest, like to create a box. of a region of interest. Like for example, this box here, just the middle area like this. This is where I want to look at only. You can also type in the coordinates here instead of just playing with the size of the box itself. So there's those options that you have. Again, do region of interest. I'm going to turn this one off. But I do want to talk about those two guys here that I've checked. So we have classified spots and object statistics. Okay. So the classified spots is to do the classification like we talked in the PowerPoint presentation. You want to say, hey, the distance, from 0 to 10, or the intensity from here to here is blue, from here to here is green. So I'm gonna, if I turn this off, I mean, again, you cannot see this because of this pen here, but it goes down to 3 instead of 4 steps. But I am going to do the classification just to show you, how it works, like what it can do. Okay. And then the object statistic is only interesting if you have other objects that you want to know the interaction between them. Okay. So this guy, he did want to just look at the count. So let's say I don't want the object statistics. I'm turning this off because I just want the count. So I'm going to go to the next step 2 out of 3. Okay. Sorry, step 2 out of 4. And by default, it creates me like the slicer view. You have the option here. I like sorry for that. So I like to call this my little post-it. This guy looks like a post-it. By clicking this guy, you always go from 2D to 3D mode, back and forth. Okay. If you've worked in the very, very past with Imaris, you may know that in the past we only had the 3D mode. The 2D mode has been added, I think, around 2, maybe 3 years ago. It's a helpful tool, especially for surfaces. So in this case, I mean, let's look at it at the 3D view. What we need to input is the source channel. So what source channel are we looking at? In this case, it's going to be the green channel here. And we do want to give the software an estimated XY diameter. Okay. So this is not a magic number. We just need to be somewhere in the range. Okay. The software tries to estimate a good size of object of interest for you. Okay. This is hit or miss. Okay. It can be really good, but it can be totally off. Okay. So never blindly trust this number. Okay. So one way to look at the estimate XY diameter is to go into slice view. So you see at the very top, we've been in 3D view. So I'm going to go to slice view. So in the slice view, I am in a 2D view, and I'm going to go slice by slice. Okay. So remember when we created the ortho slicer, we had the ortho slicer, but we were still in the 3D environment. This time we're only in 2D mode. So anytime I'm in slice view, if anywhere I left click and left click again, I can quickly get a distance, 189 microns here. So I can zoom in, and I can find this guy, do left click, and you can see 5.97. Okay, left click, 9.6. Okay, I can do it on a few of them. 7. This guy, 10. Okay, so I mean it's an estimation again. So you don't need to do like I'm gonna test it on 10 and create the mean. I typically just do it once. I mean, you can do 1 or 2 and then see what it is. But you see, like 9.94 is actually not bad. I mean, we were in the range of around 9 or 10, something like this. So if I put in 9, if I put in 10, or leave 9.94, there's not going to be a difference. Okay, so I'm going to leave the 9.94 here. And then we have the background subtraction is checked on by default. Okay, we don't have too much flexibility here because it's just taking this number in. When we're talking about the surface, I will talk a little bit more about background subtraction, but essentially it is to remove some of the background, the smaller particles, to get a better segmentation result. Okay. So going to the step 3 out of 4 by clicking next, you can see here, if I rotate, it placed me the little spots now into each of my microclear cells. Okay. See them here. You can do a quick test or like a check to see if it got each of them. You can also go with the post-it into the 2D view and see, okay, check this one. It didn't capture this one, but maybe in a different plane. Yep, it is here. Okay, this one, same, a different plane. So for this particular one, I think the 3D view is a little bit better to quickly verify, okay, did it capture all of them or did it not? Did it lose one of them along the way? So there's a filter step, the step 3 out of 4. So by default, it's a quality filter. The quality filter is an intensity-based filter, okay? So meaning that if I zoom in here and I see like, let's see, this guy here. Can you see it? Okay, can see this guy? It's obviously not a microglial cell. It's maybe some background or maybe some that's cut off or something, but I do want to capture this, okay? I can force the software to include dimmer areas, okay? So I can place a slider and you will see it will populate, probably it will start with this guy who's a little bit brighter and then go to this guy. So if I drag the slider, you see, it's populating out this one first, and then this one, if I also want to keep it, see? But the more you go, the more it's going to pick up noise and things, like where there's a change from dark background to brighter foreground. You see, like you can go and I can even go and do too much. And obviously this is not a real count here of my microglia. Okay. So you can also do the other way around. You can only focus on the bright ones, but then you lose those guys here. Okay. So you probably cannot see this here, but this guy, it's a little M for manual because I changed it. It changed to manual. If I click this M again, it goes back to A, which is the automated. So my recommendation is to trust the automated. What I do is if it didn't pick up one or if something happens, I typically go back and change things here, adjust my parameters, but rely on the automated to have least amount of human bias into my analysis pipeline. Okay. So basically, there is ways and times where you have no choice and you have to place a slider. Okay. But if I can avoid it, I try to go back and change things. And even if it doesn't pick up one or two, that's typically like one error that I personally, depends on each of the researchers, could neglect because it may be it's better comparable to a second and a third and a fourth and a 100th data set. And it's a systemic or just, I don't know what the systolic, I don't know which one it is, but it's an error that continues on from one image to another, but it's more comparable. Okay. If you have just one data set, you can also manually add spots afterwards or delete some spots. Okay, that's also not a problem. So this is the filter. I will rely on the automate. I will not change anything. And I will go to the last step here, which is the classification step. Okay. And since we don't have too much to go for yet here, I will use intensity as my classification parameter. So I'm going here into the drop-down menu, and I'm going to choose the mean intensity mean of channel 2. The red one is channel 1 and the green one is channel 2. Intensity mean of channel 2 here. And I will place a threshold, for example, 130. So the dimmer guys are blue and the brighter ones are purple. Okay, like this. And I can also add more classes. So if I click the plus button here, I can click another one here. And I can click this, like the very bright ones are now green. Okay, so I have a distribution of those guys. So I can, it's also beneficial to rename or label them at this point. So you can click on the blue box here. Instead of class A, you can call them dim. Those guys I can call, for example, medium. And those guys I can call bright, okay? Like this. And then I can finish this up. And this is my spot object. It's finished now. I have a distribution as well of intensity values, okay, in the green channel. And once I finish this, you see a bunch of tabs appeared here, okay? So we have a lot of tabs here. I do want to go briefly through all those tabs to finish up the spots. And then we can do the surface after lunch break. The surface builds up on the spots, so I don't have to re-explain everything because we already saw a lot of things with the spot. I'm just going to point out the difference about the surfaces, okay? So here, the first one is typically a gimmick. I mean, you can do scale center point, or you can change the scale of the sphere. Who does not like super huge spheres in their data set? So typically I leave it at 1, maybe I reduce it to 0.5, but I leave it typically like this. Where it gets interesting is the second point here on the top one, we have the recompute button. So in case, you know, you say you didn't like your classification, you want to redo it, but you don't want to do everything from 0, you can click on classification and it jumps back into step 4 out of 4, okay? And then you can say, I didn't like the 190 as my cutoff, I prefer 200. So I go to 200 and I finish it up, okay? And you have the option to jump into different steps of your creation of the spots, okay? So I did jump into this one, and at the bottom you have the creation parameters, okay? So this is what you use to create the parameters, okay? So you can see the 9.94 here, and even our dim, medium, and bright classification, our classes. So you can save those parameters down here for batch and reapply them on a different data set later, okay? Laura, is the lunch ready? Okay, so I would say this is a good time to stop and we reconvene after break.
And we are going to take we ask some questions. I love questions on the school, really in my
Pause the recording. Pause. Okay, awesome. Okay, let's continue the Imaris session here. So I am gonna talk about, you know, like we did the spots here for the microglia. So the next instance, this researcher wants to know the distance of each of those microglia from the vasculature here. So we're gonna be creating a surface of the vasculature. We're gonna get distance measurements between spots and surfaces, between surfaces and surfaces. And then I will talk a little bit more in detail about colocalization. And I want to finish this up with a filament tracing example about all the new features that came in Imaris 10, how filament tracing is faster and better now than before. And this should probably get us right at the 2 p.m. mark, okay? So, but before that, I do want to quickly finish the spots, like the little tabs that we have. We stopped at the second tab where we got the creation parameters to like do our batch routine, redo it on a different data set. So I do want to go to the other. So the next tab is the edit tab. I mentioned this before earlier. We can add individual spots manually or delete spots. So here in this edit tab, I can go in and zoom in and you see this little speckle here. I can shift mouse wheel, sorry, control mouse wheel to the size and then shift left click to add a spot. Or I can remove spots like this guy. I mean, it's clearly a microglia, but I can remove spots as well. And then control Z, just undo. Undo is everything you've done. So it brings the spot back, okay? Here you can also turn on object statistics if you didn't turn it on during the wizard, okay? Because remember, like the next step, this person wants to know what is the distance of each of those microglia towards the vasculature. So we do want to have object to object statistics. So I will turn it on now, okay? The next tab is the classification tab. This is where yeah, question? So you can either, you know, as you mentioned, I mean, for those on Zoom, there's a question like how we can select multiple spots and how we can do things. So just one clicking will click on one spot. If you do shift clicking or control clicking, you can select multiple spots individually. If you can change the cursor here from pointer select mode to circle select mode, or click escape. You see escape. In the circle select, you can select, you know, multiple. You can make the circle bigger with control, like this. Okay. And then also, I mean, I don't want to spoiler alert for the filament tracing. We have new now in Imaris 10 swipe select. If I have control, I can swipe select like this. Okay, but yeah, spoiler alert. So I will talk about swipe select more when we talk about filament tracing. Yes. So you have to be in circle select mode, and then you hold the control key down, and you just with your mouse click, you click those. Yep. You're welcome. Any other questions? Okay. So this is the classification. So here we can already get a count based on classification. So we can see we have 119 bright ones, 33 dim ones, and 191 medium ones based on our classification. We can add more classes here and do more stuff. Okay, so this is where we work on the classification. Then we have the filtering. The filtering, we did already use the quality filter, which is an intensity-based filter during the wizard. But we can add new filters here. So we can say, okay, I do want to filter on intensity mean of channel 2. And I do want to only keep, you know, the brighter ones. And I want to remove the dimmer ones. So I can duplicate the selection to new spots. And now I have a new spot object. These are all my spots. And the new spot object only has the bright ones that I selected, okay? So just briefly, the difference between, I'm just deleting what I did. The difference between the filter and the classification is kind of like the filter, you know, removes some of the things and lets you keep some of the things. The classification just color codes them. Like maybe you're only interested in large guys, but then you color code them green, and then the small guys you color code them blue, and then you just work with the green ones. I mean, it's preference. I mean, sometimes you do want to completely remove them if it's like noise, but sometimes you want to keep them as 2 or 3 populations. Then you use the classification instead. Okay. Then the next tab, this one is probably the most important one, it's the statistics tab. So first and foremost, we get the total number of spots here at the bottom or up here, 343. So that's the result that we wanted to get. How many cells do we have? 343. Okay. But where I spend most of my time, I mean, is in the details section here. And then you can look at the average values. Okay, so you get the minimum number, the maximum, median, those kind of things, sum. But I work mostly in the specific values. This is where I can look in specific individual objects and get their statistics. Okay. For example, let's again use intensity mean of channel 2 here. And you see this is my table. And then here's my data set. So I can see this guy here, what is its intensity? So I can left click and highlight it. And it jumps here and tells me 200. And I click this guy and it jumps here to 167. Okay. You can also go the other way around. You can click in the table here and say, hey, which one is 210? You click and one of them turns yellow. Okay. So you can go and say, hey, where is it? Here. Okay. Or you click one guy and you have no idea where it is. You can click the button on the right hand side here that says zoom and center viewing area to fit selected object. It just jumps directly to the object that you have selected. So the 2 ways that you can go. Okay. By clicking on the name here, you sort from highest to lowest. So you can go and see, hey, which one is my lowest, my dimmest guy? You can zoom in. See, this is my dimmest guy. Probably also not a real microglia here. But there's a different story. But you can see, okay, this is my dim guy. You go all the way down, 240. Which one is my brightest guy? Yeah, this one is pretty bright. So you can, these are the ways to interact here in this statistics tab. To export the statistics, we have very modern, the floppy disk down here. We have a single floppy disk. You export just the statistic you see as XLS, CSV, XML, okay? So you, in this case, you're exporting only the mean intensity of channel 2. The multiple floppy disks here next to it exports all the statistics into one file. So you will have all those statistics that you see here, they will be exported for each of those objects. Okay, so these are the options that you have here. Any questions about the statistics? Okay, so then we have the color. This is the next tab. On one hand side, we can, you know, say the labels, deactivate the labels, so everything goes to one color, okay? And then we can choose the materials, so we have 4 materials to choose from spots. Maybe we want to do them more transparent, okay? Or choose one of those materials. We have more options with the surface than with the spot. We can also change the color to a simple color, okay? Or we can do object ID, where each individual object that has a specific ID gets a specific color, okay? Like this. What I do most here in the color tab is the statistics coded, okay? Statistics coded, you can use a statistic to overlay a heat map on top of your spots, okay? In this case, for example, again, let's do the mean intensity of channel 2. So you get a gradual heat map. You have a legend down here on the bottom right. So I'm going to place it here. So you can see like the dimmer guys are like purple blue-ish, and the brighter of our cells are like orange red. Okay, so you see a gradual heat map. So the difference is the classification. You tell the software, okay, from here to here you're green, from here to here you're blue, from here to here you're red. Here it just takes the minimum and the maximum and it places a heat map overlay between those. Okay. And then lastly, we have the MATLAB extensions. So you can include your own MATLAB extensions that we have, but Imaris comes with some MATLAB extensions that our support team and sometimes our users create. And we want to release it with Imaris directly, just to get it out there quickly. The more those MATLAB extensions are being used, they become natively available in the Imaris software with new releases. Okay. So this is spots. So any questions? I'm done with spots. Any questions about spots? Yes. Yes, you can have a plot, and I will talk about plotting in more detail after the surface, if that's okay. Okay, we're going to jump into what's called Vantage to do a variety of different plots. So also the spatial plots I'm going to talk about and object-based plots. Yeah. Okay. Any other questions? Is it when you do like a batch processing, or this is regular? For each statistic is in a different folder. Do you know CSV or XML? Okay, maybe I don't know. Honestly, maybe you can try CSV or in the statistics. In the preferences. Yeah, I could look it up for you, but I don't know right off the top of my head. So maybe we can talk about it later. Yep, thank you. Any other question? Okay. So let's quickly do a surface. Okay, so we're done with the green channel. So I do want to look at the red channel here. And I want to create now a surface. So I'm going to create this surface object here. I'm going to rename it to vasculature. Okay. And this time I'm not going to do any classification. I will leave the object statistics on because we do want to know the distance now between those spots and the surface. So I do want to have this checked on. No classification. So I go to the next step. Okay. So this is my so this is my vasculature. So I'm not going to change anything. I just want to show you what happens if we go right away. But we have a lot of like it looks a little bit different here. You know, the first step looks very similar to the spots. The second step, we have first what we call like the channel is the same, like we had in spots, but here we have a smoothing of the surface detail plus 3 different thresholding techniques. Okay. So the rule of thumb is the absolute intensity is used if your intensity of the object of interest is homogeneous. Okay, all of them are like bright, all of them are dim. Most of the times you have probably some objects that are dimmer, some are brighter that you're interested in. That's where you can use background subtraction, the local contrast. Again, this is when we have dimmer and brighter structures of interest. And then new, we have the lab kit for pixel classification, which is the machine learning segmentation. This will help you for more difficult data sets to segment and since we introduced it last year, this is what I use like, I don't know, 80-90% of the time. So that includes the least amount of human bias. It gives typically the most accurate results, and it's also a quick way to get a good result for sure. Okay, I want to talk about these, but let's just leave absolute intensity. The surface detail is smooth is typically, I mean, its default is 2 pixel widths in XY. Okay, depending what your file size is, 2 pixel widths in XY is what it populates, because the software assumes everything that is 2 pixel or less, you're most likely not interested in, because you do want to at least have the adequate resolution to resolve them to more than 2 pixels. This is obviously not always the case. Okay, so sometimes you do want to you have smaller objects that are like 1 pixel or even less. Sometimes, I mean, not recommended, but it happens. So that's when you want to change this. When your object of interest are within the range of 2 pixels. Okay, what it means concrete, I'm going to show you in an example, because let's say I just don't change anything. I just go to the next step. So it creates the segmentation. So this is what you can see. Yeah, it created segmentation. So we enter 3D mode. It looks pretty good, I would say. I mean, you can maybe see there's a little bit of under segmentation. If you zoom in, okay, you can probably see it, but you get more information in detail if you go into the 2D mode. Okay, here you can get a better idea. This is a good example here. You can see this area here. This guy is too smooth for my liking. Okay, so in this case, if you want to more accurately represent this based on the size, because in this we're in the realm of 2, 3, 4 microns, I would say this is where the smoothing comes into effect. So let's say you can turn it off completely. I know some people don't trust the smooth, they just hate it, and it's fine too. But I feel like if you have at least a little bit of smooth, the result looks much better and the process works much smoother. Okay, no pun intended. But the result will be the same. Okay, I mean, it's not gonna change the underlying conditions behind the raw data. So I will typically remove it from 2 pixels to 1. So instead of 1.99, I just go to 1. And if I go next, you can already see it's much better here. Okay, it gets a little bit more under segmented here. You see that? I can go with a slider here and adjust the threshold, no problem. And the result is good, it will look good and is good, but you may have done 7.7 and then maybe your neighbor has done 8.93 or something. So there is a human bias component that comes into it. So that's why, again, remember, I try to avoid it. I try to go with the automated and see maybe I can do a different one. Let's try the background subtraction. It tells you that we need as an input the diameter of the largest sphere which fits into the object. Okay, what this concretely and in basic English means is the smallest structure of interest. What is the size in XY? So I go into slice mode again. I look into like here, maybe smallest, more or less. I mean, it's 4 microns, I would say. And this is what I input here, 4 microns. Again, this is not a magic number. It's just an approximation. What is here like a smallest structure of interest? And then I hit next. We can see it's a little bit more of a under segmentation here. So we lose more things. We can still go up and look pretty good, but we still include the human bias here. So this is a great example, typically they like to show, where the machine learning gives you a lot of flexibility and creates a much better, result in this case. Previously, we had to use the slider, which is okay, but with the lab kit for pixel classification, so if I start this guy here up, it connects the bridge. Let's hope it works, because it remember Stoyan, it didn't work earlier because of the HDMI connection. And also could be a problem. You never know. I mean, this should go to 21%, so I see it goes to 15. I already know it's not going to work because it goes to 21. It says it could not communicate, so I would just try it again. Still just 15. Let's see if I can maybe send this image quickly to Fiji. Does this work? No, I mean, you can, I mean, if you want to say, fill the gap. Talk for 2 minutes.
So I would think because you're asking.
Yeah, I mean, most of the times, even when I have just an HDMI cable plugged in, it doesn't work, and then I go to the hotel and it works perfectly. We had the same issue this morning. HDMI cable was connected, then I unconnected it. I did my tricks. Okay, looks like it worked. I know. Let's see. I did my magic, and then it worked, and then we connected it back again. But I don't want to take too much of the time, so I'm going to try it one more time here. It goes to 21. This is already a good sign. Okay, it did work now. So this window pops up, which is a lab kit window, okay, and it popped up twice because we're so happy now that it's working. So we have this window here, and basically what we want to do is, okay, maybe I ask this way: has anyone used the machine learning in Imaris before? Here, nobody. Okay, so just try it out. It's pretty cool. So you go to pen, you click on the pen, and then you tell the software what is background and what is foreground. Okay. So I click on background. I just say this is background, this is background, this is background. Okay. I typically do 3 strokes of background and then the same with foreground. Okay. I will change the color from red to green because the channel is red. So I'm going to zoom in a little bit. I'm going to tell the software this is my foreground. And since the name says it already, it's pixel classification. So you can really classify on individual pixel level. So here you can get individual pixels, 1, 2, 3 pixels, 4 pixels. But yeah, you basically tell it this is foreground, and you know here as well, this guy is foreground. Okay, I typically just do 3 strokes for each, and then you hit left pixel classification, play button, and it will just do the classification based on what you told it is background, it's foreground, and it's an iterative process. The software will learn from step to step. Okay, it won't probably do a perfect job right away because it's like with your kids, you tell them once and they will still do it wrong or will do it something. You have to do it, tell it again and again to make it better. Okay. Again, so you go in here, you see, okay, it's quite okay, but it's not perfect. Like you see this dim guy, so you say bad software. This should have been foreground and not background. So you go into foreground and you just tell it, and then I hit play again. And it will learn from the first step and the second step now, and will try to do a better job. Okay. And you can go on and on. Typically 5 to 8 iterations gives you a great result. Okay, you see now it did the connection, but it over segmented. Okay, again, bad software. You have to go again and say, in the background somewhere here. Okay. I'm just going to do it like, I mean, I'm not doing the perfect job here just for the presentation wise, but this is like the basic principle. You go iteration by iteration. So I'm doing 3 iterations now. I'm going to stop after this one, even if it's not perfect, but it should be pretty good. I mean, there's things here that are not perfect, but you do want to check the whole thing here. And then also, like I'm in presentation here, and most of the times if I do the presentation, I just show it on one slice. Do go up and down the C stack and see maybe it looks good in this slice, but maybe in a different slice, the segmentation didn't work as well. So you can see here. Okay, so it's quite good. I mean, I think it definitely can improve this, but let's say we're happy with what we see. We click this button, compute result and send to Mars. And then it tells us it will take 1 minute to bring it back to Mars, while it is also progressing here in Mars itself. Okay. Currently, it is doing the integration. LabKit is like it is a separate instance. It is not directly in the Mars, but we're not duplicating any data. It's a seamless transition. So even if your data set is 40 gigabytes, it doesn't duplicate the data. You don't have 40 gigabytes in the Mars, 40 gigabytes in LabKit. It's just sharing it seamlessly between those instances. Okay. And this is just because we want to release it as quickly as possible. In one of the future releases, this will be integrated natively in the Mars. Question? Mhm. Yep, absolutely. The question is if there's something that you want to omit, it's maybe the same intensity. Yes, you can absolutely do it, like based on shape, based on proximity to another object. So the software will learn. Sometimes you have like objects, they're all the same brightness, but you don't want the smaller ones. And of course, you can do filter later on, but you don't need to do filter. You can use the machine learning to get rid of everything you don't want right away. Okay. Sometimes you have, a specific shape, like if the rounder they are, or they look like a star, you want to keep those, then you paint them as foreground, and the ones that are the same brightness but don't look like a star, you tell the software its background and it will do this. It's also a good way to fill holes, like for example, if you have a vessel where the outside is really bright and the inside is hollow, you can tell the software that all of this is your foreground, even inside, to fill the whole vessel with volume. And then you get the segmentation of the whole thing rather than just the outside of the vessel. Okay, you can already see this looks pretty good. I mean, here also, I like it. So I go to the next step here, where the filtering step. So there's some stuff that I captured that I do want to remove. You see those round structures here. I could have told the software this is background beforehand, and then I didn't need to do a filter. But we do have the option to do the filter here, and I do the filter on volume, and I filter out those. You see those, all of those small guys here. I'm going to filter them out based on size. That's going to keep the larger vessel structure. And then I'm going to finish this up, and I have my vasculature here. Okay. So this is now my vasculature. My surface is done. Here's my microglia. I have also different tabs. Okay. They are a little bit different, but mostly the same as with the spots. So we have here, this one is the same where we can jump into any recomputation step. We can store the parameters for batch here, same as with the spots. But we do have the option to manually add structure, so we can paint in structures ourselves, because before we could just place spots. Here we can paint structures in there. We can also remove things like, for example, this guy here. Let's see if I find something small like this guy here. I can click and say delete. Okay. Also here we can turn on and off the object statistics. But again, I turn it on in the beginning. So it's good to turn on because I want to do the interactive statistics. We have classification, same as with the spots, but we didn't do it this time. We can filter also, but we did it already in the wizard. We filtered by the volume to get the smaller guys out. We get the statistics, okay? Here, so now we have statistics like surface area, volume, things that we didn't have before because we had spots. And then we have the color. So we have more materials, like I mentioned before. So we don't have just the 4 that we had with spots. We have also like this one looks kind of nice for like a vasculature, or we can make it transparent if you want to see, are there any of those spots inside the vasculature, like this guy here. Okay. So if I go back now to my microglia object here, I can go into its statistics, and under specific variables, a new statistic that popped up that wasn't there before because we didn't have the vasculature. That's called the shortest distance to the surface, and the surface is equals vasculature. So if I click here, I get the distance. I mean, it's micrometers. Sometimes mine doesn't display it if I'm also connected to HDMI, but it should say micrometers here. So it's the distance of micrometers of each of those spots to the surface of the vasculature. So you can click on this guy and say it's 29.4 microns away from the closest vasculature surface. Sorting it by highest to lowest again, you can see 78. This is the one that is the furthest away from any vasculature, makes sense. And then we have negative values for those that are partially inside the vasculature. Okay. And then we can export those. Okay, so you can see like the microglia is obviously not a spot. It's not a sphere. It has a distinct shape. So if you do the distance-based analysis like I did here in this case, or like this researcher wanted to do it, the distance from a spot to a surface is always from the center of the spot to the outside of the surface. Okay, but if you wanted to like include like the processes that the microglia have, and they're not as resolved here because it's not like a high magnification that I have in this image, but I do see some processes of obviously here and here. But I do want to include those, and when I have from the outside of the surface to the surface, I would have to use surface instead of spots. Okay. So anyways, I would have done a surface anyways, but I did want to start with spots to create this nice little story and help you guys to understand spots as well. But what I would have normally done is I would have created surfaces, I would have double clicked here, microglia, and I would have done the surface of the green channel here. Okay. And just to go about here together as well, I mean, just want to quickly again show you if I use absolute intensity in this high smoothing, because if I go in here and you see what I'm interested is actually the processes. And the processes here, they are like 2 micrometers in diameter. The 2 micrometers is like here with the smooth, I would smooth away all of those processes. And we can see it right away if I do a little just default segmentation. Oh my gosh, I did not do default. I did this by, I did not want to do the lab kit, sorry. So cancel. Cool, at least worked. So I want to do absolute intensity. So you can see already like how the segmentation looks like. It's encompassing everything. So I don't want to do this. So in this is one of the cases I would turn off the smooth completely. Okay. So even reducing it will not give you too much of a good result. So you can already see like how much better this looks, but not perfect, because the main reason why it's not perfect is because I use absolute intensity and we don't have homogeneous intensity. Our cell bodies are much brighter than our processes. Okay. That's why we have like, it's not as close here. So in this case, what I want to do is I want to use background subtraction, and my diameter of the largest sphere which fits into the object. Remember, this is the smallest diameter of interest. In this case, the processes. I will put in 2 micrometers, 2 microns, and then the result is much, much better here. Okay. But no need for machine learning, I would say, in this particular case. This looks already pretty good. But if I go into the 3D mode, you can already see there's a lot going on here. Okay. There's a high likelihood that objects are touching each other. Okay. So I do want to use the split touching objects tool here to create individual objects. What it does essentially is it creates a spot object within my surface wizard to determine how many objects do I have and how many splits do I want to have. So basically, I'm using the spots that we've done before already here to create only surfaces of those spots. Like it's an AND function. Only where there's a surface segmentation and a spot was inside there, we are resulting with a microglia surface. Okay, like this one is not there, this one is not there, this one is just this. So there's no need for a filtering step because the spots essentially replaced our filtering step, meaning we have 343 microglial surfaces. Yep. So this is our result. Now, when I go into the microglia statistics here, I have 2 new statistics that pop up that we didn't have before with the spots that are, I mean, we have the shortest distance, which we had with spots, but the 2 new statistics are overlap volume ratio to the surface equals vasculature, and overlap volume of the surfaces equals vasculature. So these are essentially the object-based colocalization. It means like overlap volume ratio gives you a percentage. What is the percentage of each of those microglia of its volume that's overlapping with the vasculature, or the volume itself? Like how many cubic microns of this microglia's volume is overlapping with the vasculature. Okay, so these are the 2 statistics you can get. And this is the vasculature. Oops, this one. Okay, so next step, I'm going to go into the advantage for the plotting and everything. But before that, I'm done with spots and surfaces, the general basic process. And does anyone have any questions that are unrelated to like graphs that I'm going to talk about here? Anything about the process of spots and surfaces? All good? Awesome. Okay, so I do want to go now in Vantage, as I promised. So this is our plotting tool. Oh, yeah, that's a question. Yeah. Yeah. The diffusion gradient? You mean like in a like with fixed law in a so there is no way to define it directly because it's not like a console like a CFD or like yeah CFD software. It does use diffusion, which I'm going to show in the graphs, to create a random generated statistics that you can compare with what you're actually having. There it's using an underlaying the diffusion law, but it does not directly do those kind of things in Imaris. Okay, so there's also not like fluid flow properties and those kind of things we cannot calculate in Imaris. That's more like a for a CFD program. So if I go to Vantage here for the statistics, so I'm going to focus just on the microglia here. So we have 1D view. I mean, this is just simple 1D plot. I mean, the shortest distance to the vasculature maybe. So you can plot just the distance to the vasculature. You can see our different populations, so classification that we've done, the bright, the medium, and the dim here. So that's actually something that I did want to show too that I forgot to show. So if I have the microglia here in the statistics, I have the shortest distance. If I export it, I also have the set one here as a statistic. You can see bright, medium. The classification will also be exported. So this is like you can have two statistics that you can correlate kind of in your export already. So those classification will always stay at any statistic that you have will be exported as well. Okay, going back to Vantage. So this is just one statistic, nothing special, nothing fancy. Same with the 2D view. You can plot on the x-axis, for example, the shortest distance to the vasculature, and on the y-axis you can plot maybe its intensity mean of the channel 2. Okay, so you're plotting intensity versus shortest distance here in this plot. Okay, but then where it gets a little bit more interesting are like spatial view and objects view. So in terms of spatial view, what you see here is a histogram count plot. Okay, so we're plotting the number of the spots versus the shortest distance to the surface. Okay, so here the cutoff is 0. Everything to the right hand side here is kind of away from the vasculature, from the surface. Everything to the left hand side is here are those spots that are overlapping, that are like those microglia that are overlapping with the vasculature. Okay, and it's based on a number of spots. So it's a histogram count plot. Okay, so another way of looking at this is a probability density plot, where we graph the probability where to find most of our microglia in this data set in relation to the vasculature. So you can see, for example, here between like 0 and like 23 is where we would find, from 0 to 23 micrometers is where we would find most of our microglia in this data set. Okay, and you can compare this with a complete spatial random generated data here. Okay, so this is a complete spatial random generated data, the Gaussian curve here, and it takes all the underlying like inside in the programming. It takes the same amount of spots. It does the calculation, and you can compare the random generated data with the actual data that you've selected, and you can already see that there the real data is closer towards the vasculature than the random generated data, meaning something is attracting those microglia. There's some form of attrition happening between the microglia and the vasculature. And then this is where you can just ask yourself more questions like what's the underlying reason behind this, how can I implement my next experiment and so on. Okay. Real quick about exporting statistics in general as well. So and those graphs, you can do a snapshot like we the snapshot. Then what you see is what you get, the statistic, like you see this guy here. Or you can export as an SVG, which is a vector graphic, and you can just modify some of the things in like vector graphics program like Inkscape and change some of the font and things like this and thicknesses. Okay, this is the spatial view, and then we have the objects view. So this is my favorite part in Vantage. Okay, so for example, if we look at the surfaces, you can see down here it says step 1 out of 2. It's kind of a mini wizard here. So I'm going to look only at the microglia. I'm turning off the vasculature. Going to go to the next step. And then you have a variety of different plots that you can do in the objects view. So one of them is a gallery view. Okay. This is where you can plot each of the microglia next to each other. And you can sort them any way you want and color code them any way you want. Okay. So let's say I want to sort them. I mean, what's the easy way? I mean, obviously volume, size, the small one here and the larger ones down here. Okay. It's just a nice view. If you've seen those, you may have probably seen those in publications. This is how they do it with the gallery view. There's so many different types of gallery views where you can also bring in the color. So you can sort by volume, but color code by different statistics, maybe by intensity mean of the channel too. Okay. So there's a lot of potential. There's like very little limitations of what you can do here. Just what you can, how you present your data basically. You can choose the columns and rows, all this. You can also change the scale. Okay, sometimes maybe the little ones are like 1 microns and the large ones are like 50, and you want to have more of an appropriate scale. You can do this as well. So there's a lot of things that you can do here. And you have obviously here your legend as well, this guy, and you can do those things. Then also what I like is a scatter plot. Okay, in the scatter plot you can do, let's just do volume versus shortest distance as one example here. Instead of having a boring X or a boring like cube, you have the actual shape of the microglia in your graph that you can use like this. Okay, I mean, it's very convoluted here, but still, I mean, it's a nice way of showing this. But there's also different ways that you can do those plots here in many dimensions. So if X, Y, and Z color, or even here, if I go into, I think this guy, nope. And lots of stuff. And it's very crunched here, you see, because of the resolution that I'm sharing it. It should be better on your workstation. Okay, which one do you want? And to grab this one here. So you have a multitude of dimensions where how you wanna, show your data. So you can say X is the volume, Y is the shortest distance, Z I want to do by, I don't know, the sphericity, how round they are. The scale I want to do by surface area, and the color I want to do by distance from origin, maybe. Okay, so you have those 5 dimensions here to plot your data in here. Okay, so again, a lot of things that you can do, and then you have multiple legends here and scale and all this. Okay, any questions about Vantage? Yeah, there's a lot you can do here, but the best way is to just go on and play with it. Okay, how are we good at the time? Good, good, good. Okay, so this basically concludes this data set. I want to move on to another data set. Any just general question about anything that you've seen? Anything unclear? Okay, awesome. So let's move on to a little bit more of co-localization, and then I want to do the filament trace. Okay, so we did the surface-based, the overlap co-localization kind of already with the microglia and the vasculature. I'm going to use this cell demo image here for the co-localization. It's just a basic image, but it shows kind of well how we can do the pixel or the intensity-based co-localization. So I'm turning off the nucleus. So I want to see what is the co-localization between green and red channel. Okay. So we have the colloc tab up here, the colocalization tab. So this is where I'm going to jump in. And I don't know if you've ever used it, but typically the first time people see this, they get super scared because there's a lot going on. Okay, let's see what's happening here. So when I boil it down to how I do it, okay, because there's a lot of stuff that I never use. So how would we do a colocalization here between green and red channel? So the first thing is you want to look at channel A and B are your two channels. So channel A is the green one. Channel B I will change to red. Okay, so these are my two channels. So by default, this slider here, you see, the histogram is in the middle, in the center. Okay. So if I zoom in here, you see those areas here that are white. This is the current colocalization at default. I haven't done anything, so obviously this is not right. This is the colocalization. So if you place this, they never work actually with the 2D histogram, because if you take those sliders here, you see the two histogram changes. So I'm just here. So if you go here with the slider and then here, you see that the colocalization changes and more of your data is colocalized, okay? Based on where you place the slider. Of course, I don't want you to just arbitrarily just play with the slider and say, hey, 100% colocalization, PhD done. Nope, don't do that. So don't do that. Just I want to show you how you can do it with the least amount of human bias, okay? Because colocalization will always, when I mentioned it, always have some form of human bias. It's impossible to reduce it to zero, but with the software you can reduce it to a minimum, okay? And there's plenty of papers that talk only about bias and colocalization, so I don't want to talk more about it than what I just said, but I just want to show you how we can use the software tools to reduce this, okay? So I don't play with the sliders, I work in the image here. So we go into our image, in this case, and it's doing it in 3D, okay? So we see one slice only, but it's doing it in the whole stack simultaneously. So if you have a 2D data set, it works the same way. It's just one slice. If it's 3D, it does it in the whole 3D slide, okay? So I start with the green channel. So I'm going to turn off my red channel. I'm going to look at the green channel. What you need to tell the software is, what is your dimmest green signal that is still considered real, okay? So you go ahead, and again, you know your data set better than anyone else, okay? So you go in here, and for example, you say this area is super dim here, it's still real, or maybe background, who knows? Let's say it's background, so that this is probably the dimmest area that's still real. Then you left click here, okay? And it encapsulates this area, and it places the threshold for you here, okay? And then you do the same thing with the red channel. You look at the dimmest red signal that is still considered real, and you do shift left mouse click, okay? Left mouse click for channel A, shift left mouse click for channel B. So I go into channel B, this is the red channel, and I say this guy is still real, so I do shift left click. You see it places me this threshold automatically. And now what is white here is our co-localized area, okay? Based on the input that I gave the software about our dimmer areas that are still real, okay? So this is what you do in this area. Then on the right-hand side in this area, you see the colloc estimated volume statistics, okay? So here you see already Mander's coefficient, Pearson's coefficient, how much is the green channel overlapping with red channel, how much is red channel overlapping with green channel, okay? So it says colloc estimated volume statistics. So it says estimated volume statistics. So never ever publish any of the data you see here, okay? If your data set is small, estimated and real values are exactly the same. But if your data set is large, if you're working with light year or something, and multiple gigabytes, the software tries to give you a quick estimate here. Then there's a difference. I mean, the difference is typically minimal, but there's a difference. So that's why don't publish those estimated. You need to calculate the real values first, okay? You calculate them by clicking on the right-hand side here where it says Build Colloc Channel, this button here, okay? So you click Build Colloc Channel, and based on the thresholds that you find here, it will build you this co-localization result channel. It's literally a new channel, in this case, a fourth channel that's added here. Okay. If you click on its name, it opens up the statistics here. These one are the ones. And if you compare those, it's going to be the same because it's a small data set. Okay. It's only different if the data set is large. Okay. So these are the values, and it tells you threshold A, B, percentage of volume A above threshold, material A threshold, Manders, Pearsons. You may ask yourself, okay, what volume, what's material? Why are there two Manders? Why are there different Pearsons? I definitely tell you what each of those means. I mean, I don't know by heart what everything means, but I can tell you what most of it means, and you may forget in a week or two. So the best way that I can show you is once you're in this here, you right click to get show help and then left click on show help. And this will bring you this tab colloc statistics, or you can click here on the highlighted volume statistics, and it will explain everything. What is volume? A, B, what does it mean? How is each of those statistics calculated? How is each of the Pearsons or Manders calculated? So we can reference it in a presentation or publication as well to the actual formula as well. Okay, so this is the best way to see, get a reference of what is happening in this tab. Okay, so this is the colloc statistics here. This is all that I do here in this tab. If you want to like do colocalization between like more than two channels, then you would need to use the result here of those two channels, and then do the colocalization of this new channel with, for example, the blue channel in this case. Okay, and then you can continuously do more. Okay, but you can in the colloc tab you can only do two at a time. Okay, so this created literally a new channel here. So if I go into the 3D view and turn off the other channels, you can see I have a colocalization channel in 3D as a new channel where I can create a surface out of. Okay, so I can get volume as well of the new surface and so on and so forth. Okay, so there's a lot of things that you can do here. For example, I mean, is there some colocalization between blue and this? I mean, maybe, I don't know. But you could also do masking. Okay, I did not talk about masking yet, but masking is pretty powerful tool in Imaris. So I did want to touch up on masking now real quick before we jump into the filament trace. Probably is the last thing today, so I can give you 5 or 10 minutes for question at the end. So I could use this new channel here to mask into the blue channel, for example. Okay, in order to do masking, you do need to have a surface. Okay, so I create a surface, and I will turn off those guys. I will look at my new channel that I create, channel 4. Let's do absolute intensity. So I can see this is definitely too smooth. So let me just turn off the smooth completely. Okay, and then you can see how pixelated it gets. So maybe I do need a little bit of smooth. Maybe like this. But it also doesn't need to be perfect. It's just as an example. So this is like kind of what I have. I'm gonna finish this up. So this is what I've extracted as my colocalization channel. And it may not overlap with blue, maybe a little bit. So what I can do now is I can take this surface and use it as a cookie cutter and cut into any channel that I want. Okay, I'm going to use it to cut into the blue channel as an example. So I go into Edit tab here. In the Edit tab, you have the Mask All option. I click Mask All, and I will cut into the blue channel. By default, it sets everything outside of the surface to 0. Everything that's inside the surface stays the same. Okay, so I'm going to use the default. And what it did is it created me a new mask channel. Oops, that is only the blue. Right now, you only see the blue inside of my surface, inside basically of the color red channel. Okay, like I will increase the intensity to see it. Yeah, so only the blue that's inside in those guys. This is all my blue. This is just blue inside those guys. Okay, and you can do the other way around as well. You can cut everything inside to 0 and everything outside stays the same. Or you can create a binary image where you say mask all, everything outside 0, but everything inside I want to have a binary image. Just I typically do 100 because 100 is easy, nice number to remember. And then you can see this is binary. Basically, binary means we have one color 0 here and one color 1, or in my case 100 inside. Okay, this is also helpful if you want to filament trace, hollow vessels, for example, to create a channel first like this. Okay. Any questions about co-localization before I jump to the filament trace as the last part? All clear? Yes. Okay, so the question was if we have like multiple cells and we want to have like co-localization per cell in the region. There's multiple ways to approach this problem. So you can, if you want to automate it, you can use the cell object, okay, and you can use within the cell object, you can use surface overlap, like with the microglia. This will give you percentage of overlap per cell between different things, but it will not give you Manders or Pearson's coefficient. But this is something that you could batch process. You can apply it on many images. The other way is you can create your region of interest beforehand and then go into the co-localization tab here and use a region of interest here to mask. Okay, so for example, just quickly, if I go in 3D view, so let's say, I have one cell only here, but let's say our nucleus here, this is our cell, and we have maybe more cells, okay, but I can do a surface of this nucleus here really quick. So next, blue nucleus, good. I do only want the big one, so here. So just created, you see this surface here. So let's say this is my cell and you want to look only at co-localization between green and red inside the cell, okay? It could be more, it could be multiple cells, but I'm just having one here. So you would create a new channel as well. So I go and do like we did the masking here, mask all. And it doesn't matter which channel I use. I mean, I can use green, for example. I do inside to 0, outside to 0, inside to a binary value, like 100. So you see this new channel. This is my region of interest. I go to the colloc tab. And now I use this. Again, we have green and red, but I'm going to use this new channel here as my masking, meaning you can see here. Now it will look at the co-localization only inside this region, not outside. So again, if I have green and red, I'm going to choose this to red. And okay, I'm going to do arbitrarily here now. Okay. You see, it does only co-localization here, but not here. This one does not count. It's only inside the cell. And then you do like we did before, you do build colloc channel. And then we have this new co-localization channel. I go 3D view and turn off everything else. So now this is the co-localization only inside the cell. And you could have multiple regions of interest. Does this answer your question? Okay, perfect. Thank you. Okay, anything else? Okay, good. So let's go to Arena. So we have half an hour left. I'm going to do filament tracing now. And I'm going to go away now from the demo data set. Again, if I open those up, if you go to edit and image properties, you can always see how large they are, like 5 megabytes. It's pretty small. This one's a little bit larger, but also not too much. So image properties, 230 megabytes, okay? So I will go now to this guy here. The neuron data set. And this one is added image properties. So it's 1.2 gigabyte. Okay, it's not super large, but it's still, you know, I'm still on a laptop. Okay, it's not a high-end workstation like you have available at Emory here, the core. But I do want to see, for those of you who have used filament tracers, just take a look at the time. It's not going to be instant, but it's going to be much faster than it used to be. Okay, who here, the participant has used filament tracer before? Okay, okay, cool, awesome. So I'm definitely going to focus on just what we see here, but I'm going to point out also the little differences between, I mean, there's a lot of differences, but like the major differences between what I've been done in the past and now. Okay, so first of all, so this is not a demo data set, it's from a customer or from a user. And it's a nice data set to exactly show what I want to show with Imaris 10. There's different other data sets that we can do. At the end, I do want to show vasculature really quick as well, but I do want to use this to do the step-by-step process, okay? So there's more, I mean, we have more channels, a lot going on here, but I'm going to focus on the red channel here. I already created a surface, okay? I created two surfaces. One that is just the big guys, the major guys, and then one, this guy, that includes the fine areas here, okay? But I do want to use this as an example to exclude those finer areas here, okay? I do want to only work with basically with those guys here, okay? So I would always recommend, if you do filament tracing, do a surface as well. I mean, it gives you the complete overview, because there's some statistics you cannot get with filament, like the total volume of everything you can get with a surface. Also, something that is not explicitly stated somewhere, but the surface can help you in the filament tracing as well, okay? So what you want to do is, in your surface, you want to make sure that the object statistic is turned on, okay? And then when you create a new filament, you also want to make sure that object statistic is turned on, okay? So even though it doesn't explicitly state it anywhere, if object statistic on the surface is turned on and the object statistic on the filament creation is turned on, it will use the surface as a reference for filling the scale, like after doing the tracing or filling it with volume, it will use it as a guide, okay? Inside in the back here, it doesn't state it anywhere, okay? Just pro tip here, okay? It is not necessary. You can still create it without the surface, but it is helpful and it is a little bit faster as well, okay? But you do not need to clean up your data set because in the past, using filament trace, I always recommend do a surface and then mask with the surface, mask the channel to just make the background 0 and only inside the surface what it is. So this is not necessary anymore, because now the filament tracer is thankfully faster, thankfully using multiple cores. In the past, it was a sequential process, meaning it was dependent on the clock speed of your workstation. So the clock speed, the faster your filament trace, but sequential. Now it's using multiple cores, parallel computing, making it much faster. Okay, one of the big differences, faster. Okay, the other difference is, I mean, we mostly like the vasculatures were always kind of neglected. There was more focus on neurons and like the tree-like structures. Now everything is together in one here, one thing. So the autopath or like the threshold, they're all taking the same amount of care now. So everything is integrated, so to say, okay? Basically, the first thing you notice is this little icon. So there's 6 different possible types of structure that you can have to extract, okay? So we can have the soma and dendrites, and spines, no loops. Here there's loops with soma, and then there's no soma and loops. So the vasculature is this guy here, because we have typically interconnections and we don't have a soma. But sometimes, I mean, why do we have spines? I mean, sometimes you have just this branch that you image at a high magnification, and you have spines, but you don't have a soma because it's just part of the neuron, then you take this guy here. Okay, no soma. But for this, I will take the basic one, this guy here, soma and dendrite. I'm not gonna go into the spines for now, but I'm just gonna go with dendrite, okay? Again, object statistic, I wanna turn it off because I wanna use the surface that I've already created, okay? And then you can see it's 10 steps. So it's a little bit longer than spots and surfaces, but the benefit here is the ones who've used filament tracing before, typically at the end, there was a lot of editing. So sometimes you had to like remove a thing here, connect some things here, like post-processing after the wizard, there was a lot of touch-ups and stuff. And using machine learning in the wizard, we want to remove those post creation steps, because all those post creation steps are not batchable, because everything you do manually, you cannot batch from it. Now, if you use machine learning tools to mitigate those in the wizard, you can batch process it, meaning you can finish this and apply it to 100 images and will work with the machine learning, okay? So I'm gonna go to the next step. Okay. It goes from 2D to 3D. So this step 2 is the soma starting point. So we're creating the starting point because we selected, we have a soma, this is my starting point, okay? So there's two ways to select the estimated diameter of the starting point, okay? The traditional way, like I showed you before, is we can go to slice view, find our soma, and then left click, and then we have 14.2 here, okay? And we can type it in here. Or it tells you here pro tip. When in pointer mode, use control middle mouse wheel, scroll to adjust the point diameter, okay? So it means you see this box. If I use control and mouse wheel, the box gets bigger, the number here gets bigger. The box gets smaller, number gets smaller. So I can go on top of this guy and try to see, okay, the box looks like this will fit, and then it populates it for you, okay? So we also, I mean, it's not necessarily like a limitation to click here and do this, but the intention is to reduce the number of clicks and to reduce the number of windows kind of back and forth between 5 and 3D view. We want to keep you in the 3D view all the time to make it as fast and seamless as possible, okay? Also, we have now pro tips here. This is something that will come in all of the modules and objects, also for surfaces, for spots and future releases, because there's shortcuts everywhere and it's hard to remember all of them, and you have to go and look them up. Maybe you have a cheat sheet or something. We do want to include them as pro tips directly here so you don't have to remember them all. So it started again with the filament tracer with Imaris 10, and then it will go on. Probably my assumption, and I don't know it yet, but is that the cell object will have the same similar treatment for next, because unfortunately cell is still limited by sequential processing. The cell object is not parallel computing either yet. So this will also hopefully soon get machine learning plus parallel computing in it. Okay. So here we have the larger diameter. Okay, so we're fine. The step 2 out of 10. So I'm going to go to the next step. So here we're at step 3 out of 10. So this is the starting point, and obviously we have one starting point, which is good. We don't want more. Okay. And then we have the option to calculate the soma model. I can turn it off. It will reduce to 9 steps. Okay, but I will have it because I do want to show the difference. So I go to the next step. So I can use either a soma or a starting point. Okay, the difference is in the starting point, the dendrite, the filament trace, the length is from the center of this point to the end of the dendrite. With using the soma model, it's from the outside of this surface, from here to the end of the dendrite. So that's the difference. You see, like, I mean, this may not be the perfect. You see, like, maybe it's not exactly like you want it to be. You don't have the option to change it directly in the wizard here for the filament, but it tells you as a pro tip here, you can create your surface externally as a surface and then import the surface into the filament object as your soma. Okay, so you're not limited with what you see here. In the wizard, you are limited, but you can create it externally and then import it as well. Okay, I'm keeping it as it is here. Okay, so I'm going to go to the next step, which is step 5 out of 10. So here is the seed point. So basically, we want to create little spots which are our seed points, to trace along those filaments, in this case the dendrites, okay? So another difference from Imaris 9.9 to 10 is now we have multi-scale points, okay? In the past, in 9.9, we had just one diameter. And guys know, I mean, one size fits all is not always viable, especially for vasculature. You have sometimes thick vasculature and thin vasculature, but even dendrites, you have thicker and thinner ones. So now we have a range. So we have thinnest diameter and largest diameter, okay? In this case, for example, if we take a look, it is not necessary to have different diameters. So if you still have, you know, like if you say, okay, 0.9 is my thinnest and then 1 is my largest, you know, it doesn't make sense. It's going to be a faster and better experience if you just keep just having one, that's the thinnest. It's only if you have a big gap, okay? Because it's even if like one is 1 and the other one is 1.5 microns, it's still in the same range, okay? So really, if there's a big difference, okay? So in this case, I don't need to use multiple, but I'm going to show you an example at the very end where you definitely need to use multi-scale points. Okay, so again, it tells you pro tip how to adjust the thinnest diameter and how to adjust the largest. So the thinnest is the same. We do control mouse wheel. So take a look here, control mouse wheel, you see like this. And for the largest, you do control alt in the mouse wheel. Okay. So I'm just using one. I'm using just 1 micron here for all of them, and I'm going to go to the next step. Okay. So you can see here it's placing me the seed point. Okay, along my trace, or like this, okay. Also here, but I don't want this, but that's okay. I can train the software in the next step. So what you need to be careful about or know is it will trace to the last spot that you can see. Okay, like for example here, it will trace until here, it will trace until here. So it won't trace all the way down here because we don't have a spot here. Okay. Same here, it will stop the trace here and not go until here. Where else do we see something like here? For example, the same thing. Here, the same thing, it will only trace until here. So you can add manually spots by shift left clicking, okay? Or what I like to do is I increase the threshold, you know, to create more spots, okay? You see? Like the spot wasn't there, I go further and the spot is here, okay? Just make sure that you have the spots here so it traces all the way, okay? It will also include more spots in general. You can see like more spots appeared here and a lot appeared here and then also some appeared here in the background. But that's okay because we'll later on machine learn train it. Which ones we want to keep, which ones we want to remove. So this is actually not by dragging this histogram slider here, this is not directly creating any human bias. It's just we want to create more spots, but later we teach the stuff of which ones we want to keep and which ones we won't. Okay. Also, you can see it has it places some spots in the spines here. You see this guy and this guy. We don't want to have them in the spines, so we can also control or shift. Sorry, what is it? Shift left click to remove those. Okay. But it's also, I mean, a tedious process to go and do all of those. I do want to do it in the machine learning step, in the next step. Okay, so there's no need to go and do this anymore. Okay. So we have 2 machine learning steps. One is to classify the seed points, and the other one is to classify the segments. Obviously, I can turn both of them off if I want to, and then I only have 7 steps. Okay, but I do want to show you each of those machine learning steps here. Okay. Also new, we have the segment diameter smooth strength. Okay, this is like how your dendrite would look like. I mean, some people, and I think it's probably not the majority, it's more the minority, like to have their dendrites looking like sausages, like super smooth. But most people do want to see, you know, the actual shape of it. So this is a good middle ground. This is basically the default, like 9.9 and previous versions were. But you can increase the strength to make it super smooth, or you can decrease it to make it even coarser. Okay. So let's go to the next step, to the first machine learning step, and you can already see. I mean, this is not the most time-consuming step, but this is one of them. So you can see 90%, So it's taking some time, but it's definitely much faster than it used to be. Okay, so we created the seed points. Okay, so now in this machine learning step, we teach the software which are the ones that we want to keep and which ones are the ones that we want to discard. Okay, so basically what you do is you go in here, you click this guy, turns yellow, you say discard. You click this guy, keep. This guy is fine. Click this guy, discard, okay? And then you will teach it and it will learn, it will just classify everything for you, okay? You just do a few, probably like 25, 30 per one of those. And then you can click train and predict, okay? Obviously, like what I'm doing is super tedious, just clicking and keep and discard. So we go to circle select, and this is where we do our new swipe select, where we say we do the swipe those guys, keep this one, discard. We go in here, say that all of those guys swipe, 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 discard, and swipe, 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 keep. You can also shortcut keep and discard with the keyboard A and D, so you can make it even faster. But yeah, you do a few of them. You obviously don't do, as I mentioned, all of them. Just do a few. This one keep. And again, as I mentioned, I don't want those. Okay, you can. I mean, it's just to show you. I want to remove them. It's a nice way to show you how the machine learning works, because we want to discard those guys here. Discard, and then we want to keep them. Keep, and we want to keep a few more here. These guys keep, and then what I'm going to do is, now that I have like 31 and 41, I just click train predict, and it will label all of them for me. So now all of them are either red or blue. Okay, and this is where you go in and see, did the software do a good job or not? It's an iterative process. Like, let's go in here and see how well the software did. Okay, so looks mostly good. Probably the spines will not be good. Okay, so you see the spines here? Yep. So bad software, you do this, discard, and then train and predict, and it should do better now. And it's an iterative process. And again, not good enough, so discard. And then let's see what else we have. Check, like here, for example, I do want to keep those actually. Keep, and then maybe I want to keep this, I don't know, let's keep it until here only. Keep, and then those, I mean, those I want to keep. Actually, those are all keep. Okay, and then train and predict, and then it's going to learn from each step and try to do a better job. Okay, and then here did keep those, and then again, it's up to you. I mean, as I mentioned, I didn't want to keep them. Discard. This one, I mean, I do want to keep, I guess. And looks good. Okay, so it looks mostly good, I would say. Okay, and then you can go on and on. I mean, this is a step where you need to invest some time to get a good machine learning recipe. You can save it for batch and then apply to a second, third, 10th data set and make your life easier. But to create an initial pipeline, it will take some time, okay? But it will pay off in the end if you have many data sets. If you have just one data set like this, nothing else ever again, then it's maybe more even easier and quicker to do it semi-automatic, to like almost manually trace them than using this. But this is definitely for batch processing. So once you did this and you say, okay, I like what I've seen, you click the next step. Okay, now let's see. Now it's the longest step. So just take a look here at my progress bar. Again, this is a 1 GB data set, and I'm on a laptop. So it's definitely not going to be instantaneously, but it's definitely much faster than it used to be. Even on high-end workstations, 1 GB data set will give you problems with time. Okay, I'll just give it a few more seconds. Okay, and it's already done, so definitely much faster. And I can already hear my fan, so it's working. But it's much faster. Okay, so this is the second machine learning step. Step 8 out of 10. So we're almost done, almost there. So this is where beforehand we did the seed points, which were the individual points. Now it's connecting the seed points to make the segments, okay? And the segments, it's the same thing. Some of them keep, and some of them discard. And you can see those guys here, the connection between those. This is what I call the guitar strings. It connects different dendrites, okay? Why does it do it? It's because it's doing much faster than parallel computing. It's doing a blockwise processing. So it starts somewhere. It doesn't know where it's ending at the end. So it's going blockwise. So it has those connections. And then once it connects the puzzle after it's done, it has the connection, but it knows, okay, there was nothing in between. So it knows it and it will take red immediately. If this bothers you, you can always turn off the red and just look at the green, okay? But you can already see like this guy here, there's something missing. You see this? So this guy should have been keep, okay? So that's why you do now. You go in here, say this one keep, this one delete, and so on and so forth. So same procedure as before. You just take a look and see which ones you want to keep, which ones you want to remove, okay? And you do the same thing. You can do train predict. You don't have to do it, all of them, and it will learn. Again, this is another time-consuming step in the beginning to create a good pipeline, okay? There's different ways to look at it. I mean, sometimes it may not be too easy to see, hey, what's going on here, which ones to remove, which ones to delete. You can always go into the 2D view as well. Okay, this can help you as well. Okay, and then you in settings you can also change from the cone to cylinder or even to line. Okay, sometimes just looking at the line it's easier, and then you can look at this section here, and you can make an extended section, meaning you can make it thicker here. So extended section meaning instead of it being 5 microns, you want to look at a section of 10 microns. 10, so you're seeing more. And this can help you to see, okay, which ones to keep, which ones to discard. Just a few ways to help you how to better, use those tools that are available in Imaris, okay? But I don't want to spend too much time here in this step. I mean, I think you understand what needs to be done here. And I won't be able to do a perfect filament trace in just half an hour that I'm showing here with also going step by step. So let's say we like what we see, okay? So I can go to the next step. The next step here, 9, 10 is the tree build, okay? So this is where we build our tree, and we can also connect gaps, okay? So we can define sometimes, there are some gaps in the filament trace, and we can tell the software to connect those gaps based on the maximum gap length, okay? So I'm not going to do anything here. I'm just going to go to the next step. And then this is the last step. This is where we have a filter based on length, okay? So typically, whatever we've done, maybe we've not done the best job. Like for example, if I turn on the channel, like here you see those guys. This is probably a spine that I haven't fixed, but it's just a tiny segment. But we know, like if the segment is below 3 microns, it's probably not a real segment. It's probably a spine or something that's caught by accident. So those red dots here, we will be removing, okay? And you can define the length, okay? The default length is typically things that are in the spine realm. Like spines typically not longer than 3 microns. So you can see this. I'm removing those guys, and I'm done. I've created this filament trace. Again, not perfect. I've already created some beforehand that are better, but this is your filament trace. Now you can go into statistics, and you have a bunch of statistics here. You can see if I scroll up and down. We have statistics obviously on a SOMA basis, which is just the surface here for the SOMA. But then what's interesting is the segment. So each individual segment, you get statistics. Or filament, which is the whole guy. So in terms of filament, you can get the length sum, like what is the length of total length of all of those? What is individual length? What is the Scholl analysis? So here, filament number of Scholl intersections based on radius 1 micron, 2 microns, 9 microns, 16 microns. How many Scholl intersections do I have? And then based on segment, you can get segment length. Okay, so a segment is always from between 2 branch points. So if I click here, this is one segment until it branches. So the length is 68.9 micrometers. You also can get the tortuosity. This is the segment straightness. Okay, so how straight are our segments? Also new in Imaris 10 is the intensity per segment. So you can look at the intensity of each of the segments. It was not directly possible with Imaris 9.9, and a bunch of other different statistics that you can here see. Okay, lots of statistics. Okay, so this is what I created quickly here, but this is what I did earlier, even with spines. Okay, so even including those guys here, but then I have one as well that I did excluding those guys here, but also with the spines. Okay, and then I did one also excluding, but no spines. Okay, so any questions about filament tracing? Okay, I do want to show really quick one last image, and then I think we have seen enough for today. The Mars 10 fun. So this is light sheet data. April talked about light sheet earlier. You have the possibility to do light sheet imaging here. Pretty cool. So this is vasculature and light sheet. Look, you can see this is the original image here. And it also it's a section, obviously. I mean, edit image. It's only 13 gigabytes. Okay, light sheet typically can get really large. So this is a part of the vessel. You can see like a thick vessels and very micro vessels, like thin vessels. So this is in the past it was impossible to do it with filament tracing. You probably have to do like a filament trace of the large vessels, then the second filament trace of the small vessels. Now you can do all in just one filament trace, like this, and have the whole thing as one filament trace, and you get the whole statistics of the whole thing. Okay. Also, 13 gigabytes was a little bit challenging with the Mars 9.9 based on time and duration. Oh, yes. I mean, you can class or you can filter out as well based on filament segments here. No. Let's see, standard filament length, standard length, and then you can see like based on, and again, I mean, it's a little bit of a delay because it's 13 gigabytes. I'm on the laptop, but you can see I can place a threshold and you can see based on the length. Or what you wanted to do is maybe based on the thickness. Yeah. You can go and see dendrite mean diameter on the diameter, and then you can say just right now just thicker ones, and then you can remove thicker ones or thinner ones or just classify them. There's a lot of stuff to do. I mean, this is the end. I didn't cover obviously everything that Imaris has to offer. This is an overview of what I wanted to share with you, especially about the new version and the general overview for those of you who've never used Imaris before. Hopefully, I'll see some of you in the one-on-one sessions. We can talk about your specific data individually in more detail. It's definitely very beneficial. Otherwise, you know, you have a very good team here, Laura and April and Stoyan, to help you guys with whatever needs you have. So don't be afraid. You're not alone. Don't be afraid of using Imaris, please. Anyone has any last questions? Otherwise, I think we can call it a day. Yes. I mean, you can use one and then using all the samples. I don't recommend just doing on one and saying, hooray, it will work on 100. Just test it with at least like 3, 4, 5. The more, the better, just to make it robust. And if it works on all of those, yes, just do it on 100 images, then don't worry about it. But just what I mean by this is like you create it once, like we did together, then you open a second image, and then you're applying the same filament machine learning trace that we've done, and then go step by step. It will import automatically the machine learning. You don't have to redo it, but you can refine it. So you go to the machine learning step and see, hey, it didn't work that well, just refine it, and then you do it in another one, and once you get a feel it works very well with the 5 data sets, then you can blindly apply it on the other one. So you don't have to do it again. You're welcome. Yes. I mean, typically, I mean, for any confocal images, I would suggest deconvolution if you haven't done it already on the microscope itself. And then background subtraction is we don't have directly deconvolution for light sheets. So for light sheet, I would always do background subtraction. If you have salt and pepper noise, median filter. So these are the 3 main ones that I use typically: the background subtraction, deconvolution, and median filter. Yeah. The median filter, yeah. That's for salt and pepper noise. Like if you have some grainy noise, it's a little bit grainy. Yep. You're welcome. Yep. Okay. So the question for those in Zoom is like, if we have like a microglia or something like a cell where we have the membrane stain or something, and the inside is like not as bright, like it's hollow, the same as when we have a vessel that's outside very bright because of the stain, but inside it's hollow. The regular tools, the intensity-based tools it's challenging for them for the absolute intensity and for the background subtraction. Yes, that's why definitely the machine learning does help. So this is how you fill holes, kind of like if a microglia or like any cell where the outside is really bright, the inside is hollow. You tell the software this is all in foreground, even the inside, and it will learn from it, and then you can use it to continue. But it's been done quite a bit since we released it. Yes, so this is definitely machine learning is a tool for this exact problem. Yeah. Awesome. Well, thank you everyone, and hope to see some of you guys later on. Okay.